Okay, so last time, if you remember, we talked about Sr Latch, right? We talked about NOR implementation first, and then we talked about the NAND implementation. And we basically went through this diagram, this circuit diagram, by putting through these inputs, zeros and ones, different combinations of 0 1s, and come up with this following state diagram. It's just like a truth table, but we got a different name for sequential circuits, namely the state diagram. According to this state diagram, we have S and R, right? Set input S and reset input R. And when you look at these inputs, you will realize that one input actually keeps the value, whatever the value is stored in this circuit is going to be hold. So the next value of the circuit would be the previous value. This is the hold. Actually, sometimes people call this hold state. Okay? Hold state. So we holding the value. Whatever it's 0 or 1, we hold the value. So what is hold means? It means we keep the value. Okay? So this value that you read as QT here, or Q prime T, would be whatever it was previously storing. If it was 0, it would become 0. If it is 1, it would become 1 all the time. Or how are we going to write something to this circuit? We actually use S being 1 and R being 0 to write a 0. Okay? You can actually check it if you like. By just setting S equals 1 and R equals 0, okay, that would actually make this QT 0 and QT plus 1. Okay, I'm sorry, Q prime to be 1. And if you don't believe me, you can go through this. 0, 0 makes a 1 here, and that one comes here and makes a 0 here. Okay, so it's a stable state. Okay, so we wrote something to this circuit. For example, we wrote 0, and if we want to keep that 0 for as long as we want, then we actually set R to 1. Okay, we change R from 0 to 1. So now 1, 1 input would keep that output 0 and 1. Okay, and whenever we want to write 1 to this circuit, then we change S to 0 and R to 1 so that we can write 1 to QT. Okay, Q prime T is always the inverted version of QT, all the time. Question?
Yes, and what is written on the right upper...
This one?
No, the top of that column.
This one? This one?
Yes.
QT plus 1.
Okay.
This is like next state. Okay? But that's just one way of showing the next state. Because T's are going to be always integers. Okay, I'm going to assume T to be 0, 1, 2, 3, 4. Okay? It's all going to be all integers. It's not like real numbers. Alright? The reason being, because we're going to have a clock signal and clock tick. Every clock tick would be, going from one integer to the next. Okay? That's why. Okay, so this is our next state, and this is the previous state, right? Therefore, if you set S equals 1, R equals 1, you keep this state. All right? Let me show you one example of this in a timing diagram, right? So let me show you, for example, a sample question that you may face, okay, in the exam, in the homeworks, or in the quizzes. All right? So I may actually give you S value. It's going to be a function of time, of course. So it's going to start like this and then go maybe do, kind of fancy things and then go something like that. All right? Of course, because of my drawing, that may not look to scale, but these are either 1 or 0s. All right? Okay, now we have R. This is the reset input. Let's see. All right, something like this. Okay, so this is time, by the way, right? So exactly in this particular instant, T is 0, and you go from left to right so that T starts, ticking. Here, of course, my t is real, okay, unlike this one. Okay, I'll come to the reason why I assumed integers there. But this is real t, okay? As you can see, there is no clock here, right? There is no clock. Everybody here, like these two inputs, can go up or down anytime, any real number, okay? So at any time. Of course, these are all, they're on the same level. All right, now I want you to draw qt, okay? So we're going to draw qt. This is 1, this is 0. Let me draw these as well. And I'll show you how this thing goes. All right, now, you're supposed to draw the qt, right? Now, how should we start? Well, apparently, s equals 0 and r equals 0, you see, it's an undefined state. So we've got no idea what those are, okay, until this point. Okay, so there's a big question mark here because these two inputs leads to an undefined state. In our previous class on Monday, I talked about this undefinedness, which was the metastable state, if you remember. So therefore, you may see a 0 or 1, but that would not be under your control. Okay? So therefore, you cannot use those inputs to control a sequential circuit. That's why I say an undefined. Okay? It may actually stay somewhere in between, by the way. All right? So you can actually go ahead, use a multimeter, and measure the result. It can give you 0.4 volts, for example. Or maybe it can give you 2 volts. But that would not mean anything in digital logic, right? So therefore, we don't use those inputs for the NAND implementation, by the way. Right? Okay, so this is a question mark. How about this? S being 1, so we got this time interval, right? So this, time interval, we got S1 and R0. If S is 1 and R is 0, it's you can see, it's one of those states, right? And it's a kind of a set state. You set the value Q to 0. Okay? So therefore, Q would be 0 now. Okay? It's a set, so you're basically setting it to 0 value. So you write 0 to that Sr Latch. In the next time instant, actually in the next time interval, those intervals will be, of course, same length when we talk about clocks. But we are not there yet, okay? And well, basically that's why I introduce Sr Latch first, and then flip-flops, which I'll talk about today, okay? Which are based on clock signals, not these type of intervals that I'm dividing the time into, and those are kind of non-uniform, as you can see. This is a shorter time period, this is a bigger time period. And the reason that I'm dividing that way, because in one of the inputs change, whichever does that early, I actually clip that time, okay, to create another interval. Because in this time interval, either S or R makes another change. For example, R makes a change. Although S does not, right, with respect to the previous time interval, R does. That's why I, clip the time. Okay? So during that time, I have got 1, 1. What is 1, 1? It's a keep state. It's a hold state. So what does that mean? That means you keep the previous value. What is your previous value? It's 0, so you keep the 0. Okay? That's what this means. All right? So you keep now the 0 value. Okay, let's go to the next time interval. Next time interval ends in here, because that's where you have a change in S, but not change in R. Okay? So what is that? It is 0, 1. 0, 1 actually corresponds to writing a digital 1 to your Sr Latch. So therefore, your state jumps to here, and you create this 1 now. Because you wrote 1 to the Sr Latch. What is the next one? It's 1, 1, right? So let's assume that they are equal, they are kind of, aligned, let's assume. Just for simplicity, where's my blue? Okay, so let's just assume that they are aligned. Okay, they don't need to, by the way, but I'm going to just assume that they are aligned. All right? So 1, 1. What is 1, 1? It's a keep state. It's holding it. What's the previous value? Previous value is 1. So it keeps that 1, okay, for the duration of that time interval, right, or time period. All right, what's next? Next is this. Okay, what is that? 0, 0. What is 0, 0? It's undefined. So you got no idea what this is gonna be. Okay, it may actually, this voltage level, it actually can fall down like that. You got no idea. That's why we get rid of this in the D-latch implementation, which I'll basically draw on the other side of the board, okay, in a minute. So we got no idea what happens here. So what's next? Let's just assume these are also aligned. Okay. What is this? 1, 0. What's 1, 0? It's a writing 0. So this will actually start here with a 0. Okay. And we have another time interval here, which is 0, 1. But we know that 0, 1 corresponds to 1. Okay, we got this 1. And finally, we have another, but very, very small time period here, which is 0, 0. But 0, 0 is, again, undefined, so we got no idea what's happening here. And finally, we got 1, 0, which is 0. Okay, so you start here again. All right? Since I kind of randomly came up with this question, we got those undefined states. But usually, of course, you wouldn't have those in your exam question. But, you know, I probably, you know, won't you ask kind of a, you know, a Sr Latch where you have this undefined state. Instead, I would probably ask you D-latch, or maybe some other latch or a flip-flop, where you don't have such undefinedness in this state table. Okay? Anyway, I just wanted to show you how the time, as the time passes by, how the inputs and outputs change at the output of such a sequential circuit element. As I said before, this is just an example, and we will have more complicated versions of these sequential circuit elements, and the same time, timing diagram would apply. Okay? You can basically have a complicated sequential circuit, and you can still, if you know the inputs, you can still draw the output the same way I did right here. Okay? Okay, so refreshing your mind about our D-latch, right? So we did have enable. We actually put an enable to this circuit by introducing extra NAND gates, remember? All right, we got this NAND gate as well here, another NAND gate. And then we have this and then that, okay? And so we did have S and R and an enable, right? This is an enable, all right? So if enable is 0 in this circuit, if enable is 0, that would make outputs of the NAND gates 1, 1, and that 1, 1 corresponds to hold states. So when you want to hold something, you turn enable from 1 to 0, you hold it, okay? And if you don't want to hold or write something to the Sr Latch, this Sr Latch, then you of course have to enable it. This is like a write in control signal. Okay, you can treat this as a write enable or write control. If you want to write something, you make this equal to 1 so you can have access to this memory element. If you don't want to have any access, if you don't want anyone in the room or, in the circuit, write anything erroneously to this sequential circuit element, then you disable the circuit by setting enable to 0. All right? Anyway, so what I did in our previous example, remember that we did have this undefined state. Okay, if you draw the same exact state diagram, you will realize that you will have an extra input E. All right, so I'm just gonna do it quickly. pretty quickly. So we got SR. If E is 0, S and R they don't matter, right? And with QT plus 1 was just QT, right? And if enable is 1, right? If this is 1, then you have S. If S is 0, that would make it this 1, right? And we know that if 1 and R is 0, you got a 0. So this is like the completely reverse. So, for example, we are able to write 0 here. When S is 1 and R equals 0, this would be 0 and 1. That would make you write 0, okay, because of this, negation operations. Okay, and if this is 1 and this is 1, 0, that would actually help you write 1. And finally, this would be, if enable is 1 and S and R are zeros, right? That would make it, keep it. And if it is 1 and 1, 1, that would actually be undefined. Okay, and what we did last time, that we can actually get rid of this undefined state. How? By making sure that S and R could either be 0, 1 or 1, 0. In other words, just eliminate these following the last two rows, right? Just disable this one and disable this one. How? We can just connect a NOT gate, right? A NOT gate right here. Let's just connect a NOT gate here, okay? So you've got only one input, and I'm going to call it D, okay? So therefore, if D is 0, this is gotta be 1. If D is 1, this is gotta be 0. Okay? There's no other way. So therefore, you eliminate these two rows, because S and R, these S and R, cannot be 0, 0, cannot be 1, 1. So we completely eliminate these two rows. The reason, again, that we're eliminating these two rows is because we're about to get rid of the undefined state. But unfortunately, we also eliminate some useful state here, which was a hold state. But it doesn't matter. We already have a hold state with the enable set to 0. So here we go. We have a hold state, we have a write 0 and a write 1. So these three states are capable of writing and holding at the same time. Okay? That's why this D latch is a good latch, which helps us develop these three useful properties at the same time and without having an undefined state. So we get rid of the undefined state by just putting a NOT gate in front and connect these S and R with a single input D. Okay? You see there is an enable input, D input, Q output, and Q prime output. The following picture is going to be what you're going to be seeing in the lab, in the class, all the time. I'm not going to be drawing the D latch all the time by giving you the internal details. What I'm going to do, I'm going to just put a D here and enable Q and Q prime. That's going to be my D latch. Okay? It's just like a big rectangle, two inputs, D and enable, and Q prime. Okay? What's inside? This is inside.
May I ask you a question?
Sure, please.
Can you please tell why the Q state is also compensated by this?
This one?
Yes. Shouldn't we, because we eliminated the undefined by adding the latch, and we also eliminated the keep state.
I mean, we eliminated these two, yes.
How do we compensate for the other one being eliminated?
You mean the first row?
No, the second eliminated row, not the undefined one.
Oh, yeah. So you're saying, how are we getting QT here? Mm-hmm. Yeah, the way that we get QT here is because of the enable. If enable is 0, you see these are zeros, but that automatically makes the output of these two NANDs 1, 1. But we know from the SR latch, this is my base SR latch, if the inputs are 1, 1, it corresponds to QT. That's why we're holding it. Okay? So that's why we are holding it. It doesn't matter what S and R are in this case. You can just set S to 0 or 1 or R 0 to 1. It doesn't really matter. What matters is in enable being 0 would make the output of these two NANDs 1 and 1. And that will hold the state.
So even though we got rid of that key,
This one? Yes, we get rid of this because in order to get the QT, the hold state, you have to have S and R set to 0, 0. Okay? But this structure would not allow that. Okay? That's why this is eliminated as well. But we did that on purpose because we already have a QT. You have a hold state already. So the reason that we did this kind of a tricky approach just to get rid of the undefined states.
because we can afford to lose the other.
Absolutely, we can afford to lose the other hold states. Correct. Is that clear to everyone?
Is
Yes.
the output depend on only S value?
Output depends on S and R values if you're trying to write. Okay, if you're trying to write something to this circuit, like if you want this circuit to hold 0 or 1, okay, then it would depend on S and R, because if S is 0 and R is 1, then you write 0. If S is 1 and R is 0, you write 1. If you want to keep it for as long as you want, then you set enable to 0, then it would not depend on an SNR because you can change SNR the way, incredible number of times, it would not matter because enable is 0, it will always hold the value.
For example, when enable is found, S are 0 and there is 1, it sets the value 0, right?
Yes, it sets this value to 0. In other words, QT becomes 0. As long as you have these three inputs, the QT would always be 0. Always. It's just like passing this S through the circuit, and circuit memorizes S. Okay, memorize, and you suddenly change enable from the 1 to 0, then circuit already has memorized S. It will keep 0 for as long as you want. Even though you change S and R, despite that you can change these S and R, right? The output would not change if enable is set to 0.
So it resets the 1 value and sets 0, right?
Yeah, sets and reset, yes. If you'd like to write 1, then you have to set equal to 1 and R equals to 0. The reset equals to 0. Okay? It would take a little bit, a little while to digest, I admit. Okay, so let's look at this circuit. Let me erase this nice timing diagram, which probably will draw a couple of more times just to show, because this is a sequential circuit. It has got a memory. I have to show it the changes over time, right? Because in combinational circuits, we didn't have a time concept. Because combinational circuit is just instant. When you have inputs, because of the gate delays, you may wait for some time, but it's going to be nanosecond scale. So outputs is over there. It's fast. So that's why we didn't have any time concept in the combinational circuits. However, in sequential circuits, we have a time concept, which probably makes it a bit harder for students to, grasp. Okay, so when I want to look, I look at this D-latch, and one of the things I realized that this uses, if I replace this NOT gate with an AND, this uses 5 NANDs, right? 5 NANDs. So let's just replace this with an AND, right? Remember the NAND? Right? This is a NOT gate. So we got these NAND technology mapping for the Sr Latch and use 5 NANDs. So what I want to actually focus on, this point. What's the Boolean expression for this point? Let's see. This is D, this is D prime. And what is this? This is enable. I call it E. So this is E. So what is this? This is D prime, E prime. Okay, you with me? All right. Now, I want to write this as maybe something like this. D prime E plus E prime E prime, because I can add, this is a 0, E prime E is a 0, okay, so I can add 0, okay, so it doesn't change the original Boolean expression. Okay, so what I want to do from here is that I can actually write this D prime E as, because I've got E and E here, you see, E and E, actually use distribution law to write D prime plus E prime, E, and prime, of course. Okay? It's just the reverse version of the distribution law, right? Now D prime E is here, E prime E is here. Okay? And this prime, of course, we carry that prime. Okay, now if I use the Demorgan's law from here, I can actually write it D E prime E prime. Okay? Okay, so what does that tell us? Well, that tells us that this is D and E going through an AND gate, right? And then it goes through an AND gate with an E again, because there's a prime here. All right? So what I want to do here, I'd like to draw the circuit diagram once again, because look at the Boolean expression here. This is D, this is E, this is actually D E prime. All right? But I already have the E prime here. Okay? So why don't we just get the D E prime from here, okay, and then put through E and then NAND it to create this output. Okay? So what does that correspond to? That corresponds to the following. I erase this. Or maybe I should not erase that. I may actually have to draw it here so that you can compare them. All right? All right, so let me just draw the Sr Latch, because Sr Latch doesn't change. Okay? Sr Latch, the format of the Sr Latch doesn't change. It's always this way, okay? There's no trick here we can play. Okay, so this DE is a good one. So actually I'm going to take this and connect it to a NAND. Okay? With, of course, this is going to be, you see this, let's just say another NAND here. Okay? And this NAND is D and E. Okay, so you got the DE prime. I've drawn it step by step so that you can follow. This is DE prime, okay? And then this should be this thing, and E, this is gonna be E. So let's just connect the E here. E and prime, okay? Right, here we go. This is exactly what I wanted to get. So therefore, this formalism enables us to use 4 NAND gates instead of 5. Okay? Because this is exactly giving us what we want. 4 NANDs. Okay? Just a little bit of tricky Boolean manipulations. Okay? Alright, so this is your D latch. Alright? This is what is inside. Okay? You see, you can use less number of NAND gates through this simple optimization. Okay, so now, you know, every single D latch uses 4 NAND gates. Okay, just keep that in mind, because in the future we probably have to touch upon this several times. And then we can, of course, compare the complexity based on that. Are we recording still?
Yes.
Okay. How many minutes do we have?
1 minute.
1 minute. Okay. Do you have any questions? Okay, let me erase the board. Or maybe I can keep it. Just move on to the other side of the board. Okay? Okay, now, of course, you know, D-latches are good as a memory element, but as I've shown you, the timing diagram, okay, not this one, but the previous, in the previous session, I did have a timing diagram, and I did talk about the changes can happen anytime. right? Anytime. So therefore, if you got a noise in the input of the SR latch, for example, if there's a noise in the D, that noise would be reflected upon the output. Okay? What I'm saying is that in the previous case, let's also draw some timing diagram here for D. Okay? Here we go. This is my D, let's say, and enable. Okay? And output Q, right? So I actually divide that into, segments. You see, the reason that I draw segments is, it has to make sense to you at this point. Okay, here we go. Here we go. Okay, these are the segments that I'm interested in, time segments. Okay, I have got 0, D is 0, and enable is 0. So if I want to draw the state diagram for this, I have D, can be either 0 or 1. What is QT plus 1? If D is 0, if this D is 0, I have to also put E, right? The E. So let's see. Here's my eraser. So we got D input, E input, and the next state, right? 0, 0, 0, 1, 1, 0, 1, 1. If enable is 0, we know that it's going to be hold state. If enable is 1, D passes, right? Remember, D is now S. So 0, 0. Okay? And if you got 1 and 0, you got another hold state. And if D is 1 and enable is 1, then you write 1. So instead of writing this way, we probably have to write D and E and QT plus 1. And if E is 0, D, we don't matter. It doesn't matter. So it's going to keep the QT. And if E is 1, Q is 0 or 1, we write 0 or 1. Okay? It's pretty simpler version of the same state table. Okay? Or maybe you want to write, just eliminate E, or maybe not eliminate E, but eliminate these zeros and ones because it's just identical to D. So all you want to do is enable QT plus 1. If enable is 0, it's going to keep the state. If enable is 1, you got DT. Right? The input. It's much simpler. As you can see, the SR latch and its corresponding flip-flop, which we will call it D flip-flop, is the easiest sequential circuit element you can ever find. Okay? Because of this state table. Let's come back to here. You got 0, 0. When you have 0, 0, it's going to hold the state. Do we know the state that we're holding? Because it's the original, that it's like t equal to 0 case, so we got no idea. That's why this is going to be a question mark. It's not like undefined state, okay? We're probably be holding something, right, in the beginning. Maybe in the lab you remember the chips, or maybe not, because you haven't done the lab 3 yet. But the chips are usually set to 0, okay, as an initial state. So therefore you can assume this to be 0, but anyway, from a theoretical perspective, let's just assume it's a question mark, because we don't know where we are. However, when you go to the next one, when enable is 0 and D equals 1, it's a still hold state, so we don't know that again. How about this? D is 1 and enable is 1. Well, we know that it's a 1. So we write something like 1 here. Okay, now from now on, you would have no question marks at all, because there's no undefined state. So you would always expect some 0 or 1. Okay? Keep that in mind, because with D latch, we don't have any undefined state. So we got this E and D. So we basically, what this is doing is, whenever enable is 1, it passes the D all together. Okay? All together. So this D is copied all together to here. Because whenever enable is 1, it will always copy D to the output. Okay? That's why we have the copy here Okay, and it's here also. Okay, but then we stop. We copy D to the output whenever enable is 1. Okay, and then we stop because enable now becomes 0. Whenever it becomes 0, it's going to hold. But what is it going to hold? It's going to hold the latest value that we were holding, which is 1. So for this time period, it will always hold it. Okay? It will always hold it. Why it's holding 1? Because that was the last value that we were copying to the output. That's why it's holding this 1. Okay? You can just simply see that by just going to this specific time instant and come back here and see this is a 1. And that 1 is carried along for this particular time period. Okay? And finally, of course, all of a sudden the enable becomes 1. That would actually start copying the Q again without looking at what the previous value was. Okay, so you see it's all 1, so it's going to copy all 1 here, so you will see this. Okay? So, now coming back to my previous comment. I said that noise is also copied, correct? So let me show you an example where the D input could be noisier. Okay? As you can see, D is kind of ideal here. It basically, specifically, it holds a specific logic 1 or logic 0, but therefore, I can actually do the following reality show. Okay, this is reality. Okay? This is what you're going to see in the input. So, when you use an SR latch, what you're going to see is, okay, these are question marks, but whenever enable is 1, it's going to copy D. So you're not going to see this nice waveform. Instead, you will see something like this. Okay? Okay? Something like this. And then, it sees this, you see that now it goes exactly on that specific point, so that we were lucky. It will hold this value for as long as we need. For as long as E equals 0. And then, it's began copying it again. Okay, so that's what you're going to see at the output. Okay, you see the original waveform, and on top of that there is an added noise. And added noise is also passing through the sequential circuit, because the way that we design the latch is copy D to the output, whatever that D is, when enable is 1. When enable is 0, then keep the last value of the D, okay, and keep that value for as long as the enable is 0. Okay? This is problematic, guys. We don't want to really pass the noise this way. Okay? Instead, what we could do, we could basically only look at the rising edges and falling edges and make a decision instead of copying. Okay, what does that mean? For example, let's take rising edge. Instead of the entire 1, we're going to take only the rising edge and make a decision. For instance, when enable is 0, we don't do anything. We just hold it, but there is no value to hold. It's just question marks. Whenever you have a rising edge, you go to that specific point in time, and then you realize that this is your D. Okay, it's close to 1. And then you keep that value for as long as you got another rising edge, which is right here. Okay? Or maybe falling edge. So which means you're going to keep this value, okay? Let's just draw Q bar, let's say. That's my new Q in the rising edge mode. In the rising edge mode, I'm going to have question marks, and then this is going to be some value here, but I'm going to keep it right here, a specific 1. It's a straight line now because I'm actually focusing on a specific time instant, not the entire, period. That's why I get rid of all these noises, etc. Okay, and then when you have a falling edge, you basically hold it, for example. Okay, and then you go to another rising edge, you go to a specific point here, for example, it's about 1, maybe a little higher than 1, and then you keep that 1 now. Okay? I'm specifically talking about, of course there's going to be some little noises, okay, when you do these changes in your state, but what I'm trying to point out is that when you look at these waveforms on the top one and the bottom one, you realize that there's going to be a lot of noise in the top one, which was the latch implementation. This one would be the flip-flop implementation, and this would have less noise. Okay? Of course, here the results do not look alike. The reason is being this enable and D, there is no synchronicity between them. They are asynchronous, as you can see. That's why latch can work in asynchronous environments, but the flip-flops, they don't work in asynchronous environments. They have got something called clock, which I'll introduce now. And based on that clock, they make decisions. Okay? And all digital circuits, synchronous digital circuits, use flip-flops instead of latches because of that noise characteristics. Can latch be used in synchronous circuits? Yes, they can. But again, their noise problem is still there. So we don't want to really bother ourselves with the noise. That's why we use flip-flops. So how are we going to make this using latches? How are we going to make our circuit be sensitive to these rising or falling edges instead of the entire period? Okay, that's the question underneath that we should ask. Fundamental question we should ask for the flip-flops. Okay? So, let me just introduce you a bit more formally. Here is the clock. The clock signal is like a heartbeat. Okay? It's just like a heartbeat we have humans. We're having, without the heartbeats, can you live? No. Without the clocks, no synchronous circuit can live. Okay? So, if you use a latch, these are the places where you're going to have a change, a copy operation of the input D. Okay? How about these? These are hold states. This is my clock signal. Now I'm transitioning to synchronous circuits where clock is essential. Clock is a periodic square waveform, by the way. Okay? The period here is fixed. Okay? This is P, this is also P, and this is also P. Okay? It's periodic square waveform. And the period can change, of course. Have you ever, guys, done any overclocking your CPU? Okay, you're changing this P. Okay? You're basically shrinking the period to a smaller value, so you increase the frequency. Remember, the frequency equals 1 over period, right? So if you increase frequency, you decrease periods. Okay? And that's exactly what you're doing. Okay? Of course, there's a limitation. You cannot make it 0. Okay? Which I'll talk about in computer architecture class. Why you can't do that. All right? But of course, if you shrink this to a maybe acceptable, some acceptable time, then this would increase your operations. Because every single clock tick corresponds to a specific operation completed from a CPU perspective. Okay? So now, for the latch, we have these hold states. These are changing states where D is copied to the output. How about these? These are the hold states. Okay? I'm going to be where this clock is going to be connected to. As you can guess, it's going to be connected to enable. Okay? This enable will be connected to the clock signal. Okay? All right. Now, coming back to our flip-flops. What is changing in a flip-flop? So I still have the same, of course, clock signal, right? Now instead of having these time periods, I'm interested in the rising edges, for instance. So the flip-flop can only change in those rising edges or falling edges, okay? Depending on the design, which I'll show you two different designs, one for the rising edge, one for the falling edge. Okay, so this could be another flip-flop. These are called also trigger, by the way. Okay, if your flip-flop is triggered through these, oh sorry guys, this should be a falling edge, right? It doesn't make sense, not natural, right? If you follow the curve, it's not going to make sense. Okay, sorry about that. So this is your falling edge. Right? Falling edge, falling edge. And this is your rising edge, rising edge, rising edge. Okay? These are edges, right? Edges. And we call trigger? Because sometimes people call this flip-flops in different terminology. For example, one book calls rising edge flip-flops positively triggered flip-flop and falling edge flip-flops as negatively triggered flip-flop. Okay? That's why I'm introducing both terminologies so you don't get shocked when you read different books. Okay? So sometimes people call it positively triggered, negatively triggered, or sometimes they call it rising edge or falling edge flip-flops. Okay? Now, I'm going to draw, since now you are knowledgeable of what's happening for the flip-flops. So flip-flop, this is latch. Now you're knowledgeable about the difference between latch and flip-flop and the motivation behind using a flip-flop, the noise cancellation, right? And more stable outputs. That's also very important. Now I'm going to draw the first flip-flop of your life, which is going to be based on the latches that we already have seen. Okay? This simple D latch, which was made of 4 NAND gates, right? So let me draw it here. So we got these 2 D latches. Okay? This is my D. But I'm going to name them D1 and D2 so that you can differentiate them. So this is D1, D2. And this is clock signal. So you see that the difference between, maybe not here. This is my enable. Let me just copy exactly the rectangle I have here. Okay, and this is my Q1, Q2, and the primes, of course. All right, so there are 2 D latches now in my design. I'm going to connect the D here, and this one, exactly the output connected directly to the input of the second D latch. And this is my Q, okay? And I have a clock signal, this one, going into, as clock, as you can see, it's a periodic waveform. And this is going into enable, and the negated version or inverted version going to the other latch. Okay? And of course, this is going to be our Q prime. Okay, so this is, which I claim would be operating as a flip-flop. Okay? Which I'm going to show this as a shorthand notation as D, Q, Q prime, and clock. I use triangle now, okay, to differentiate this from this. Okay, this is a D latch. This is flip-flop, and actually this has a name, D flip-flop. Okay, D flip-flop. Now, of course, we haven't proven anything yet. I have to prove that this is sensitive to only the edge transitions, but not the changes in the enable. Okay? So let's just see. I have a clock signal, so let me just look at this clock signal. And this clock signal is going to look like something like this. Okay? All right. See when the output of this circuit changes. Okay? Now, let's just say this is A. Okay? All right, now, whenever you have a clock signal 1, okay, I'm talking about this particular time interval, right? If clock signal is 1 here, it is 0 here, right? Because of this NOT gate. So what is that 0 doing here? It's holding it, right? Whatever A is, it's going to be A here. However, when a clock is 1 here, it's going to enable this latch, and this D will be copied to here with noise because it's a latch. Okay? If there's a noise on top of D, that's going to be copied to A. But since this is disabled, right? This is disabled because of this NOT gate. It's not going to push it out. Okay? It's not going to push it out. So what is it pushing out at that particular state of time? It's pushing out what this latch was storing in the previous round. Okay? In other words, when enable was 0. Okay? I'm sorry, the enable was 1. but we don't have that yet, right? So it's just pushing out some random number. So in this case, we have A, let's say A, being equal to D, right? Let's say D0, okay? Because I'm going to just say this is T0, okay? Now T becomes integer because it's a clock, right? T equals 0, T equals 1, T equals 2, blah, 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 blah. Okay, now, all of a sudden now clock becomes 0, okay? If clock becomes 0, this would disable this latch, okay? Which means it's going to send whatever it was sending before, which was D0, right? So that means whenever this clock becomes 0, this D0 would appear in A, okay? And even if that D is changing in that particular time period, it's not going to be copied here because this is disabled. So this is going to be still D0. A is going to be still D0. Okay? But what happens to Q? We don't know here. What happens to Q? Well, since this is now enabled, the A, whatever that A was, is going to be copied to Q. Okay? So this D0 now is going to be copied to the Q. Okay? But that D0 is not the noisy version because this is disabled now. Okay? The previous D is not copied here. Okay? So if you continue the same way, this is going to be D1 and D1, and this is going to keep it D0 and then D1. Okay? Apparently the change happens, you see, the falling edge. Okay? This is going to be D0, then this is going to be D1. Okay? If you don't believe me, you can actually go ahead and, enable here and then disable here. Since this is disabled, this is going to keep the D0, so that's why you have a D0. And then this is going to be disabled, this is going to be enabled, then you will have D1. Okay? Therefore, the change happens in the falling edges. Of course, since there is nothing here, you don't see that, but you can actually go ahead and write these, and you will see that the changes will only happen at the particular falling edge instance. Okay? Because these two D latches work in alternating fashion. One is enabled, the other disabled, then this is disabled, this is enabled. And the way that they work actually cancels out the noise because this can be copied here. The noisy version could be here. But since this is disabled, that noise is not passing through the second D latch. That's why we don't have, for a specific certain time, for example here, okay, changes cannot happen. It keeps D0 for as long as that clock signal is 1. Okay, you cannot copy D here because it already kept something here. It already hold on to something here, and that is the output of that hold value. That's why, unlike the D latch, it cannot copy the D input, as is to the output. Okay, that's why these D0, these are fixed values. Okay, D0 is not like DT. It's a specific value at time equals 0. Okay. So therefore, this is a falling edge or negatively triggered flip-flop. D flip-flop because there's only one input, D. Okay? And my question is, can we make this positively triggered flip-flop? Or positive or rising edge flip-flop by simple tweak? Can you propose a tweak, simple tweak, that would make this circuit rising edge? Just intuitively. You don't have to prove anything. What's your guess? You see there's a NOT gate there which sends 1 up and then 0 to the other one.
Okay, explain first and the CFL.
Maybe we should send 0 here and 1 there, right? Yeah, absolutely. Or instead, I can actually put a NOT gate here. If you don't want to change the internal, right? Put outside a NOT gate. Because NOT and NOT gives you the original signal, right? So if you put a NOT gate here, clock, right? So you don't change the internal. This NOT gate would make this 0 and this 1. and then blah, blah. So this is going to be turned upside down. So this actually would turn upside down, so that therefore it's not going to be falling edge, it's going to be rising edge where the changes would happen. Okay? Or of course, as your friend said, you can eliminate, if you're able to, you can eliminate that NOT gate, that would be the same. Okay? So rising edge or falling edge. It's not that really critical actually. You know, the critical thing is that you should have some circuit that will have these rising edges or falling edges. Okay, whichever applies. Okay, and some circuits, by the way, have both rising edge and falling edge. You may have heard from, for example, RAM technology, DDR. Have you heard that? This is double data rate. Actually, DDR4, right? Double data rate. What is double data rate? Well, double data rate is this. Rising edge, falling edge. Rising edge, falling edge. Rising edge, falling edge. Conventionally, we have either have a falling edge or rising edge. But now, these circuits have both rising edge and falling edge, doubling the transfer rate. Okay? That's why people call it double data rate. Okay? All right, how many minutes do I have? 5 minutes, okay. Let's stop here then.